Welcome to 6.2. We're going to talk about the graphs of exponential functions, and we're going to explore them using our good old graph transformations. All right, let's get started. Well, what does a graph of an exponential function look like? Let's remember our general form, f of x equals a times b to the x. Remember, if b is between 0 and 1, that's going to be exponential decay, and that's going to be a function that's always decreasing. If b is greater than 1, that's exponential growth, and we have a function that's always increasing. So if we look at these two graphs, the blue one and the green one of them is f of x equals 2 to the x, and the other one is f of x equals 1/2 to the x. And that does not look like 2 to the x. Let's just fix that so that looks a little better. 2 to the x. Hopefully you can decide which one is which. Take a moment. All right. Hopefully you notice that 2 was bigger than 1, so that would be the one that is increasing, so that's the blue one. And 1/2 is between 0 and 1, so that is the one that is decreasing, right? All right, let's talk a little bit more about characteristics of exponential functions. All right, so if we're talking about basic exponential functions, a times b to the x, there's a couple things we're going to look at. Here's a little picture of sort of a generic increasing one and a generic decreasing one. First of all, let's think about what is the domain of exponential functions. Well, thinking back, we've talked about domain a bunch of times in this term. We keep coming on it with all of our functions. And when we talk about domain, there are two things that can go wrong. You can divide by 0, or you can take the square root of a negative number. Well, we're not going to be square rooting here at all, so we don't have to worry about taking the square root of a negative number. And we also aren't dividing because there's no fraction bars in these problems, so we don't have any domain problems. And the domains of exponential functions are -infinity to infinity, or all real numbers, just like quadratics. All right, how about vertical and horizontal intercepts? Well, unless they're shifted, they're not going to have any horizontal intercepts, but they always will have a vertical intercept. And to find that, you simply compute f of 0, or, right, we can also look at the a value, right? The a value will tell us the horizontal intercept. We talked about horizontal asymptotes when we talked about rational functions, and exponential functions also have horizontal asymptotes. If we're just looking at a basic a to b to the x function, the horizontal asymptote is always going to be the x-axis. If we shift it, that horizontal asymptote will shift as well. And we already talked about increasing and decreasing, but let's hit it again. If b is bigger than 1, we're going to have always increasing, always increasing. So the period of increasing would be -infinity to infinity. And if b is between 0 and 1, it's always decreasing, always decreasing. They don't change. They're either increasing or decreasing the whole time. All right, exponential graphs are pretty nice graphs to draw. I like them. I think they look good. Let's go ahead and look at a couple and see if we can use our skills of what we have to match these functions. I find these to be a little bit stressful when they come up on the homework assignments, but I find that if you just go one by one, you really can work through them. So I want you to pause the video now and try and figure out which of these match with each of these functions down below here. Take a stab at it right now. All right, let's go ahead and get started. Well, the first thing I'm going to do really quickly before I even jump in is I'm going to notice that A, B, and C are all decreasing. A, B, and C. I'm taking a few notes before I even look at the functions. Are decreasing. So that tells me 0 is going to be less than B is less than 1 for those guys. And D, E, and F are all increasing. So I know those have to be B greater than 1. All right, so that's good to know. Let's look at a couple other things. Well, I noticed that A, B, E, and F, A, B, E, and F all have the same y-intercept. And C and D do, and it's also bigger. C and D have the same y-intercept, but is bigger than this one, bigger than that one. Okay, so that helps me. Now if I go down and look at my functions, I'm going to start with that y-intercept value. Well, I see 2, 2, 4, 2, 4, 2. So here's my 2 with the bigger y-intercept value. So I know one of those has to be C and one of those has to be D. Now I'm going to look at my B value. And if it's decreasing, I know that the B value has to be between 0 and 1. So I know this one has to be, well, first off, I know this has to be C or D, right? Because of the y-intercept value, C or D. C or D. I'm going to write a little bit more neatly. I'm going to try C or D. And now I know that C is decreasing and D is increasing, so this one has to be C. It can't be D, right? Because it's a decreasing, a less than 1 value for B. This one is increasing, so it can't be C. It has to be D. So those guys are done. All right, so we have 4 that all have the same 2 y-intercept value. Of those, A and B are decreasing, and E and F are increasing. All right, so let's just rule those out. This is going to be less than 1, so this one has to be A or B. This is also less than 1, so this one has to be A or B. So my 0.81 is less than 1. These guys are both bigger than 1, so this one has to be D or E. I mean, not D, E or F. E or F, and also this one has to be E or F. All right, so I've narrowed this down a bit. All right, so let's go ahead. Which one is going to be, let's actually start with E or F. Which one is going to be E and which one is going to be F? Well, the base, so this one is increasing by 28% each unit, and this one is increasing by 59% each unit. So that's got to be the one that's going to grow faster because it's growing at a faster rate. So E is growing faster than F. It's shooting up faster than F. So this one has to be E, and this one has to be F. Now, I did the increasing first because it's a little bit trickier than the decreasing. Remember when you're looking at decreasing, you have to sort of, oh, what did I do? You have to subtract from 1. So if I look at G of V, this is decreasing, so 0.69 is 31% less than 100%. So that's losing 31%. And this one is losing 19%. So if you're losing a smaller number, you're going to decrease slower. So G is going to be the one that decreases the most swiftly. So that guy is going to be B. And A is going to be this one because it's decreasing less swiftly. It's losing less each time. Hope that made sense to you guys. All right, so these are a little bit tricky, but hopefully I showed you a little bit of a method for doing them. First, divide them into who's decreasing and increasing. Look at the y-intercepts and then evaluate the rates. Remember that for increasing values, the bigger the number, the faster the increase. And for less than 1 numbers, the bigger the number, the slower the decrease because you're losing less each time. All right, this is actually still video 1. We're going to stick with video 1 here. Exponential transformations are exactly the same as regular transformations. We're just applied to exponential functions. And so all the same rules apply. You can reread these. I'm going to go on to the next slide because I think it's a little bit easier to look at a graph of each of these. All right, so here's some graphs. Let's zoom in on these. So blue is my original function. So blue is my original, and it's actually 2 to the x. And if I shift it up by 1 unit, so if I go 2 to the x plus 1 as my function, that's going to be my green. And you can see that every value is just exactly 1 up off of blue. And sometimes when you're looking at exponential functions, it can look a little strange. So you have to really take a moment and analyze what's going on. So that's, again, just a vertical shift added to the outside of the function, behaves exactly like our other graph transformations. Our second example here is a shift inside the function, left 1. So you can see if blue is my original and I shift every value 1 to the left, there we go, and that's going to be my function. So this was f of x plus 1, or if we look at in function notation, that would be 2 to the x plus 1, right? So the vertical and horizontal shifts behave exactly as they behaved before. Let's stretch just a little bit, and when I look at the stretches and compressions in this example, I really like to look at the y-intercept value because that helps me the most. Remember, blue is my original, and my original y-intercept value is 1. And on my green one, my y-intercept value is 3. So I've stretched up a factor of 3. So every value is 3 times more than the value it was on the blue value. Likewise here, I've compressed by 1/3. So every value is 1/3 of the previous value. All right, let's keep going. Oh, I didn't mean to zoom in. And let's talk about reflections. Remember, minus f of x is going to be reflected across the x-axis, so every output value swaps signs and becomes a reflection across the x-axis. So if I got the output of 1, now I'm at -1. If I got the output of 2, now I'm at -2. And reflection across the y-axis, it happens inside the function. So what happened before at f of -2 now happens at f of 2. What happened to f of -3 now happens at f of 3. Every value is swapped. Right? And you can also see those because the y-intercept value is going to stay the same. All right, so let's practice this. I need to zoom back in. Let's practice this a little bit by drawing this one by hand, and then I'm going to show you how to use Desmos to help us with this a little bit as well. So first, we're going to try to draw the graph of the exponential function g of x equals -2 to the x plus 3. So first, let's draw the graph of 2 to the x. And I want to do this well, so let's see here. 2 to the x. If we plug in 0, we get 1. If we plug in 1, we get 2. If we plug in 2, we get 4. If we plug in -1, 2 to the -1 equals 1/2, right? -2, we get 2 to the -2, which is 1/4. All right, so we don't need, let's see, 1, 2, 3, 4. That should be good. 1, 2, 3, 4. And then let's go by the same scale here. 1, 2, 3, 4. 1, 2, 3, 4. Guess we have 5. We might as well use them. All right. All right. So -2, -4, 2, 4, -2, -4. Okay. And let's plot our points. So we have 0, 1, 1, 2, 2, 4. I don't want to get off here. 1, 1/2. -2, 1/4, and we know that there's a horizontal asymptote here, so we're just going to kind of do, oh, that's not so good. Let's see if we can do better than that. Oh, that's not too bad. And there's my graph of 2 to the x. All right, so there's my original graph, and I'm going to switch to a different color. I'm going to go to green here. And now let's see about listing our transformations that we need to perform on f of x to obtain g of x. Well, there's two transformations, right? We have the negative outside, which we need to do first. So we need to flip it across the y-axis, right? Because it's flipped across x-axis. Sorry about that. Flipped across the x-axis. And we have this +3, so it's shifted 3 to the left. Okay, so we need to flip every point across the x-axis and then shift 3 to the left. And it asks us to sketch g of x and label 2 points. Well, the first thing I'm going to do to just kind of help myself here, I know these transformations, but I'm going to use a little table of values to just kind of help myself with my new function g of x. I'm just going to put in a couple values. So if I plug in 0, always a good choice, I get -2 to 0 plus 3, which is -2 cubed, which is 2 cubed, and then -1, which is -8. Right? Let's plug in 1. That's -2 to the 1 plus 3, which is -2 to the 4th, which is 2 to the 4th is 16, so that's -16. So we're pretty far down already at 1. Let's see if we can get some better values here. What if we put in like a negative value? Let's put in -1. -2 to the 2, which is 4, -4, because order of operations square it first, so this is -4. That'll be better. That'll be better. I was like, how did I get so far? That doesn't seem right. And then this one is -2. And then -3 would be 0, which would be 1. And there we go. And then -4 would be -1. -1 would be -1/2. So we're just going to go along like this. And then we're going to add that. Okay, so here we go. Yeah, this isn't the greatest graph, but we get the idea. All right, so there's a graph of our new function. We plotted some points, and let's see if we can convince ourselves that we flipped over and shifted 3 to the left. So if we flip over, that would become, this point would go to here. And then if we shift 3 to the left, we go 1, 2, 3, and sure enough, that does actually work. So let's try one more. Flip over, that would take us to -2, shift 3, 1, 2, 3 to the left. So you could have done it with a shift. I think that's a little bit difficult in my mind, a little bit. All right, so here we're going to do example 3 in Desmos, and I have hidden the actual graph from you. And we're going to do the problem from the Drawboard PDF, which says to use the graph below as a transformation of f of x equals 2 to the x. We're going to write the equation describing the transformation. And so what we're going to do is we're going to use Desmos to help us with this. So we know that we need to graph 2 to the x, and we need to transform it to make this blue graph. So the first thing I'm going to do for Desmos, because we have these great graphing tools, let's use them, is I'm actually just going to graph 2 to the x. All right, there's my graph of 2 to the x. And now I want to do some transformations on this guy so that it matches the graph in blue. So what do we think the first transformation? That was what I would ask you. Think for a second, the first thing that you notice about the black graph versus the blue graph? And I hope that you notice that it's reflected across the x-axis. So the first thing I'm going to try minus f of x. Maybe that will match up. So you can actually just type in minus f of x. So that's my new guess. And if you want to turn off your first original one, you can just click it off. I'm like, okay, that looks better, right? Those guys are looking similar. They're pointing the right direction. The change seems to be the same. What do we need to do now to minus f of x to get it to match the blue one? And to me, I can pause for a second. Actually, I'm not going to say anything. Pause and see if you can figure out what you need to do to minus f of x to get it to match up with the blue graph. All right, did you come back? Did you think it needed a vertical shift? So the next one I'm going to try is I'm going to just, with my minus f of x, I think it needs to be shifted up. It looks to me like 3 because I'm at negative 1. 1, 2, 3. So I'm just going to tuck a plus 3 on the end here. And sure enough, if I click this on and off, there's my blue and there's my black one. I think this is a really great way to use Desmos to help you with these kind of examples, and feel free to do this in your homework. When it comes time to take the test, I know that you don't have access to Desmos during the test, so you won't be expected to do this type of graph transformation without a tool that you've used with your homework. All right, that's into section 6.2.